All right, we're continuing our first activity here. And we're going to do some valence Lewis structures for organic molecules. And here's a little note that'll save us a lot of time and grief. You don't need to count valence electrons for organic compounds, but you must learn the nature of these atoms in neutral molecules. So these are the big ones in organic chemistry. And in particular, these are the big two. One of them is not big at all, because every organic molecule has carbon bonded to hydrogen. That's about as close to a definition of an organic compound as you're ever going to get. You gotta have carbon bonded to hydrogen. Notice that leaves out some molecules like carbon dioxide, not organic. No. Methane though, CH4, definitely. Number of bonds hydrogen likes to make always? 1. How many lone pairs does hydrogen like to have always? None. Do that a little bit. Go for the yellow. Straight yellow. That's pretty nice. Oh, you got to wait for him to straighten out first. Straighten it. There we go. Carbon. 4. How many lone pairs? Good answer. None. Now nitrogen. Think of ammonia. What's the formula for ammonia? NH3. So how many bonds you got there? 3. That's normal for nitrogen. How many lone pairs? It's got to have an octet for nitrogen, right? Most atoms in organic chemistry strive for an octet, where there are 8 electrons around that atom. How does nitrogen get an octet when it only has 6 electrons and 3 bonds? It has 1 lone pair. Think about water for oxygen. 2 bonds to hydrogen. How many lone pairs? You've only got 4 electrons around oxygen now. You need 2 lone pairs. What about fluorine? It likes to make 1 bond, right? Because it's going to have, right, it starts with 7 valence electrons. It only needs to share 1 more, right? There's your bond. And then it has 3 lone pairs. Hey, there's a sequence there. Anytime you can use the periodic table to help your learning, it's a beautiful thing, because it's already organized there. It took mankind 2,000 years to figure out the organization of the periodic table. More than that, really. We're just talking modern history here. Okay. So, what about atoms related? Well, where would you put silicon here? Same information as carbon, right? Silicon, germanium, tin, lead. Nitrogen, phosphorus, arsenic, antimony, bismuth. Sulfur, selenium, tellurium, polonium. Chlorine, bromine, iodine, and we'll never talk about astatine, but it's there. So if I asked you, what's the nature of bromine? You'd say 3 lone pairs and 1 bond, right? What's the nature of silicon? I got 4 bonds. Doesn't have to be sigma. Can be some pi's in there, as long as the total's 4. We even know sigma and pi. Yeah, we did. We introduced that, right? Sigma's the first bond. Everything after that's a new bond called a pi, right? You'll be reading about it. Promise me. And organic chemists, when they list things like this, are giving you lots of good information about the skeleton. They've done all the hard work for you. Okay? Tell me what you think parentheses CH3 twice means. There's a CH3, there's 2 different CH3s attached to the next atom, which is a carbon. So CH3. Did you think the H's are between the C and the next C? Never. What's the nature of hydrogen? You already wrote it down. One bond. You can't have an H between any two atoms ever. Just throw that question away if you do that. H is sticking off of something, right? In this case, 3 H's sticking off of one of those carbons. I'm drawing it right now. 3 H's sticking off one of those carbons. And there's 2 of these groups. That's what the parenthesis means. They're not attached to each other. No, they're attached to the next atom. What is the next atom? This carbon right here that has no H's on it. Here's their connection to the same atom. See, there's 2 CH3s connected to the next atom. That's exactly what I drew, isn't it? Yep. And then after that, what's after that? C. Don't put an H on that atom. There's no H listed after this atom. A C that also has no H's. And then a C with 1 H. I don't care where you put the H, everybody. It doesn't matter. As long as you draw a bond to an H. Up, down, right. Don't put left. I've already used left. Okay? Going up. Notice I'm not worrying about full octets yet. Just laying out the skeleton in terms of the atoms that were given in the question. What's after the CH? What's the next atom over? C. How many H's on that? 2. Top, bottom, left, right. I don't know. I don't care. And then after that, and it's Lewis. You can't just, if you did this, you're going to lose a little bit of points if you do this. Don't draw this. Don't stop drawing. Don't do this. Lewis structure has to show every valence electron, right? There's bonds there you didn't show. So you got to show the bonds. 2 separate H's. Now we're going to use our nature of the atoms to finish this off. This carbon's done. Why? 4 sigma. 4 bonds. Period. Forget about sigma pi. Let's try to stop saying that. This one has 3 bonds. Uh-oh. You're going to put a lone pair on it? No, if you do, it's wrong. Carbon doesn't like that. Doesn't do that. I've already got the sigma bond there. Now I'm going to use those letters, those Greek letters again. I need to add a pi bond, but please don't do it this way. Don't wait. Don't stop. You do that on a test. This carbon here that has 5 bonds, I point to it and I say OV, octet violation, -1. That's not a formal charge. That's a score on your test where you just lost a point. Okay? Don't do that. You can't do that. Where do you have to put the pi bond? Between these 2, right? Yeah. Okay. Now the carbon on the left is finished. It has 8 electrons around it, right? 4 bonds, no lone pairs. Remember what I said? It doesn't have to be all single bonds, as long as the total is 4 bonds. It is, right? 1, 2, 3. What about this carbon? It's only got 6 electrons around it. Don't put a pi bond to the left. Octet violation to the left. Gotta put it to the right. And that fixes 2 carbons at once. 4 bonds to the carbon on the right now. Yay! And what's the one last thing I have to do to be finished? What's nitrogen's nature? I got the bonds covered. I need a lone pair. And I'm going to highlight it. That's all I really need to see is your answer. My highlighter needs to be thicker. Oh, that's a big highlighter. Oh yeah. There you go. And C will do below. Now, some of you have maybe had a teeny bit of experience with stick figures. You're going to read about them in section 1.6. When you have sticks that intersect, like meet at an angle, where they meet, that's understood to be a carbon. Okay? Unless a stick meets at the end where it's clearly not a carbon. Look at that. I wrote down O there. That's not carbon. But You know, if I have a stick meeting a stick, that's a carbon. So, little stick figure preview. I'll put the skeleton for that ring down here. There's a bond there. And I have double pi, sorry, the second bond there, there, and there. So that's from the top of the screen, and I copied just the ring. And another thing that I didn't tell you yet is that in stick figures, you're allowed to omit only one type of atom. And what type of atom is it? The answer is not just hydrogen. Yes, the hydrogens on the carbons are missing, but those are the only hydrogens that are allowed to be missing. Hydrogens attached to carbon are understood. So you're saying, well, how the heck do I know how many hydrogens there are then? The answer is right here. Carbon forms 4 bonds. 4 bonds, no lone pairs. If you see carbon with 3 bonds and it's from a stick figure, guess what the 4th bond was to? Hydrogen. I'm putting those on in black. Don't put a hydrogen here because there's an oxygen there. Don't put a hydrogen here because there's a carbon there. The picture above says that. But you can put hydrogens on all the ones where there was only 3 bonds showing on the carbon. I'm going to slide down a little now. Okay, and we're going to finish that one. The O. What's listed after the O? C that has no H's attached to a C that has 1 H. There you go. Now let's use our nature to finish this thing off. Oxygen's got its bonding thing finished. It's got 2 bonds. What's it missing? 2 lone pairs. Carbon can't put lone pairs to finish its octet. It's got to go pi bonds. Don't go to the left. You'll have an octet violation on oxygen. Oxygen's got an octet. Any additional electrons towards oxygen? Bad news. I think 1 pi bond doesn't finish it, but a second does. And just in review, the combination of these 3 bonds is called a triple bond. I don't really like that expression though. It kind of implies the bonds are the same, and they're not. The first one, the best, the strongest one was the sigma, and each of the additional ones were pi. Okay, so there's always 1 sigma between any 2 atoms that are bonded. Guaranteed. 1 and only 1 sigma. If there's more than 1 bond between 2 atoms, those are always, what are they called? They're not called sigma. Pi. So we have 2 pi's here. You're going to be reading about it. I know it's why are you getting a little nervous already? Now, previewed all the way to the end of the chapter. This is a very common short form in organic chemistry. CO2 in the middle of a structure. It could be a carboxylic acid or a carboxylic ester. And we don't know what that means. But the only way to properly draw it is to make sure you do one of those O's is double bonded to the C. So if you see CO2 written forward, CO2, or backwards, remember molecules don't know direction. If it says O2C, that's just CO2 the other way, right? Come on, my Arabic students are well aware of that. We're reading it that way, and they're reading O2C. Okay. Carboxylic acid or ester, in this case, I'm going to tell you it's an ester because the CO2 is followed by another C. Okay. So when we get to the end of the chapter, you're going to read about functional groups. And that's how organic chemistry is organized. That'll be its own rook. You know, the relevance of organic chemistry, functional groups. And then the whole course, when you get near the end, and then the next course is just the behavior of the different functional groups. Yeah, they're like actors in a play. Okay? So, when you see CO2, you got to just you gotta trust me. One of the O's is double bonded with two lone pairs, and the other is a single bond. Now, if it was a carboxylic acid, it would be followed by an H. Here it's not, right? It says O, the second O is followed by a C with three H's on it. And I know I forgot to finish the nature of that previous oxygen. How do I do that? This oxygen here, how do I finish it? Two lone pairs. And that down there is a carboxylic ester. And on Wednesday, we are going to do things like I give you this picture and you tell me the formula. Yeah, and right now it's easy to do the formula from down here, isn't it? You count your C's, you count your H's. In fact, well, I'll pretend I asked that question. What's the formula for the molecule? And it's always this order, everybody, for organic molecules. What are the first two important elements? Always C, and the second most H. And then you go alphabetical. After you finish with C's and H's, you go alphabetical. I think it's N, then O in this case, right? Oh, there's no N. It's just O, isn't it? There's not a nitrogen there. Three O's, is that right? And carbons, you got 6 in the ring. 6, 7, 8, 9, 10. H's, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. There you go. So I just discovered something. Technical issues in the morning section cost us 20 minutes. This is where the morning section ended. It was at the end of class. The good news is that's where we're going to end too. Okay. So we finished all our questions. We stopped.